In this section, we're going to revisit our study of conic sections. And in fact, we're going to describe conics using a different kind of equation. We're going to use polar equations to describe the conics. And more than that, we're going to actually redefine conic sections. The redefinition will help us with this new kind of equation. So we just kind of have to look at the conic sections in an entirely different way. Now, one of the fundamental ideas, besides the notion of using polar equations to describe them, is that we're going to kind of move our attention from the center or vertex of our conics, the center of the ellipse and the hyperbola. You see, was the jumping off point of our graphing. We identified the position of the center, and then we identified an A and a B value, and we structured our graphs. And with parabolas, we identified the position of the vertex. And that vertex could be identified, and those centers could be identified by looking at the equation. We had all of that information within the equation, and then we could go about structuring the graphs. Well, here we're changing our thinking altogether because we're going to reposition the conic section so that those important points, we're going to redefine the important points. Instead of being the center, it's going to be the foci that are so important in our study. And we're going to position the foci at the origin or at the pole when we talk about polar equations. Now, to do that, it requires a complete adjustment in our thinking and also kind of a redefinition of all of our conic sections. And it turns out that they can all be defined in a very similar way, and that is in terms of eccentricity. Now, eccentricity, we mentioned eccentricity associated with the notion of ellipses and the elongation of an ellipse, the relative elongation of the ellipse. But it turns out that we can associate eccentricity with all of the conic sections. And as a matter of fact, another idea is the notion of directrix, that we only talked about directrix in terms of the parabola because it was necessary for the definition. But really, there's a directrix associated with ellipses and hyperbolas as well. So let's get started with the idea of how we're going to sort of redefine our different conic sections. And then we'll get into the equation notion. Well, remember before that when we defined parabola, we said, okay, we start with a line called a directrix and a point not on a line called the focus. And the parabola would be all the points in the plane that are the same distance from the directrix and the focus. Okay, that's fine. Now we're going to define the situation this way. All right, here is our focus. Here is a point we'll call P on the parabola. And here is a point Q on the directrix. Now, we know that this distance and this distance are equal to one another. That is, FP is equal to PQ. Make this straight. That should be a straight line distance. All right, eccentricity is defined as a ratio. Now, eccentricity was a ratio before when we talked about it with ellipses, and we'll come back to it, and I want to relate back to it when we get to the ellipse. But we're going to define eccentricity here as the ratio of FP to PQ. And since those distances are equal to one another, that eccentricity number is 1. Now, let me tell you where we're going with this notion of eccentricity. It's as though we're saying that given a conic section, we can identify the kind of conic section that it is by identifying the value of its eccentricity. And if the eccentricity is 1, then that conic section is a parabola. You see, so that's why I'm making such a big deal out of this idea of eccentricity and how it is calculated. All right, let's go to the ellipse. Now, with the ellipse, remember the definition before had to do with the sum of distances from the foci. That is, the sum of, let me just draw a little segment here and here. The sum of this distance and this distance was the same for every point on the elliptical curve. That is, this plus this is equal to, for a point here, this plus that. And then for a point right here, this distance plus that distance, same as the others. So it's the sum of distances which were the same for all points on the elliptical curve. Well, now we're defining the ellipse differently and in terms of eccentricity. Well, to have an idea of the eccentricity, we're relating it back to eccentricity for the parabola. It's the same idea. We identify a focus point. We identify a point on the elliptical curve. And we think about a point on a directrix. Now, the first time we've had a directrix here associated with ellipse, but there is a directrix associated with the ellipse that lies out here. There's another one that lies over here. It's kind of an imaginary line, but it also exists on this side. Now, here's how these play or interact with one another. That in this circumstance, is it clear, go like this, that the FP distance is less than the PQ distance? You see, and that would be true for all of the points that are on the ellipse. Now, the notion of definition in terms of eccentricity, though, is this, that the eccentricity is FP over PQ, just as it was for the parabola, but all of those were, the FP, PQ were equal for the parabola, so eccentricity was 1. But here, the eccentricity, because it's FP over PQ, is less than 1. And this ratio is the same for every point on our elliptical curve. And that's the idea that gives us definition here. It is that the ratio of FP to PQ for every point on the ellipse is the same. And if we're dealing with an ellipse, then that eccentricity number, constant for every point, is less than 1. Okay, now, from our study before, we know that as the eccentricity number approaches 0, we have an ellipse that approaches a circle, and when that eccentricity number approaches 1, we have an elongation, a greater and greater elongation. Now, our eccentricity number was calculated before as C over A. Now, remember that the C and the A distances from before. It's going to be really important that we are able to recall those values. That A was the distance from the center to the ends of the major axis. B was the distance from the center to the ends of the minor axis. And C was the distance from the center to the focus points. And now the center doesn't seem to make any difference whatsoever. It will make a difference, though, if we're going to try to construct the graph, and we will be doing that in just a little bit. But our sort of center of the universe here is the notion that we are situated at the pole, you see, with the origin of our coordinate plane, or the pole of our polar coordinate plane. Now, and by the way, just to give this whole study some validity, there's good reasoning for doing this, for kind of repositioning our thinking and writing our equations in polar form. And a good example comes from astronomy, where, you know, all the planets have an elliptical orbit, and they are orbiting around the sun. Well, it turns out that the position of the sun is in the position of the focus, you see, of every elliptical path, of every elliptical curve, of the path of every planet, you see. And so in order to study in astronomy, it's kind of handy to use as the center of the universe, you see, the sun. All right, so that's kind of the one example of why we're doing this and so forth. Okay, now let's move over to the idea of hyperbola. Now, for hyperbola, our definition before had to do with the difference of distances. And now we're changing our thinking. Well, our thinking now is this, that we have a directrix, we have a focus, we have a point P on the hyperbola, on one of the branches, and we have a point Q on the directrix. Now notice that the distance PQ is always a perpendicular distance. That is, from a point on the curve, whatever curve we're talking about, to the directrix, it's a perpendicular distance, or the shortest possible distance. But here, notice the comparison of this distance FP and this distance PQ. You see, FP is going to be larger than PQ. And it's the idea that the ratio of FP to PQ is the same for every point you see on this curve. And there's another directrix associated with this focus, and that same idea holds true. That is that the ratio is the same for every point, this ratio FP to PQ. Now, it's also true that the eccentricity number is greater than 1 in the case of the hyperbola. Now, I'm emphasizing the notion that for parabolas, the eccentricity is always 1. For ellipses, the eccentricity number is less than 1, and for hyperbolas, it's greater than 1, because that's the basis upon which we identify the kind of figure we're dealing with. And we identify it that way because the equations are going to all look pretty much the same. You see, when we were talking about the equations before in our rectangular coordinate plane, we could recognize equations, and we trained ourselves to recognize equations. We put them into a certain form. We talked about the coefficients of x squared and y squared if they were in general form, and whether we had plus signs preceding those squared terms. And in the standard form, we were talking about whether or not there's a plus sign or a minus sign between a couple of fractions, and we had to have 1 on the other side of the equation for the ellipse and the hyperbola. So all kinds of characteristics had to come into play. Well, here, our equations for all the conics take one of these forms. Now, these are the equations, but let's understand that E in these equations stands for eccentricity, and P is the distance from focus to directrix. Focus to directrix, and it's important that we grip on that, because when we talked about a P before that appeared in the equation for the parabola, remember it was x squared equals 4py, or y squared equals 4px, but the p value was a directed distance from vertex to focus. And here we're changing that idea for p. Same letter, and yet it stands for an entirely different thing because we're dealing with polar equations. Okay, so p is the distance from focus to directrix. All right, now, here are our equations for all of the conics. Now, let me tell you the nuances, the differences among these. They look an awful lot alike. This one and these are the same. The difference is with cosine and sine. And we have plus minus here, plus minus here. So really we have 4 equations. Now, here's the difference. The eccentricity number, this coefficient here, will tell us the kind of figure we're dealing with. If the eccentricity number is equal to 1, we have a parabolic curve. If it's less than 1, we have an ellipse, and if it's greater than 1, we have a hyperbola. All right, that's all there is to it. Now, putting it into this form, though, requires that we have a 1 in this position, and that's going to be the prevailing characteristic that we target when we start to manipulate this rascal. Okay, if we have cosine, then we have a major axis or a transverse axis or an axis of symmetry that goes horizontally. Now, I'm thinking of it that way because the notion of cosine, remember when we talked about the exchange of rectangular x and y components in a polar form, that x was r cosine theta. So cosine is associated with a horizontal notion. And I'm associating this cosine with a horizontal notion of a horizontal transverse axis, and a horizontal major axis for the ellipse, and a horizontal axis of symmetry for the parabola. All right, so all right, that's one notion. And now what about the plus and minus? You see, well, the plus and minus pretty much tells us the side of the figure on which the directrix lies. and right over here, if we're dealing with the hyperbola, let's say, and notice that we have a horizontal transverse axis, so the equation associated with this will contain cosine. And we have a situation where, let's see, if our pole is right here and the directrix is on this side of the pole, then it's going to have the minus sign involved in it. Over here for the ellipse, we have a horizontal major axis, and so we're going to again have this cosine notion that we're dealing with. And I see that the directrix is to the right of the pole or the focus point, and therefore the plus sign is going to be involved in that equation. Over here for the parabola, I notice that the axis of symmetry is vertical rather than horizontal. So the vertical notion corresponds with the idea of sine. So it's going to be that form over there that has sine involved in it. Our focus is here, our directrix is below, and therefore a minus sign will make its appearance. Okay, we're going to become familiar with these ideas on sort of a need-to-know basis. As we gain experience with these, we're going to learn about them. But the perspective we're going to take at first in this study is to look at an equation and then analyze the equation in certain ways and identify certain characteristics and information that will allow us to construct a graph. Now, I want to relate this, though, back to the regular rectangular coordinate form. That if we had an equation that looks like this in rectangular form, I have positioned this equation or this ellipse so that the focus is actually at the origin. Now, the center of this ellipse is at 4, 0. We know the A value is 5 and the B value is 3. We could easily construct the graph. We could find the position of the center. All of those things are pretty evident to us right now. Now, all of those things that are evident to us in an equation that looks like this at this point will be evident to us as we continue our study in polar form. So all of this will just come in due time, and we'll have a good feeling for the idea of equations in polar form. And I want to say that here because this seems very confusing at this point. It probably does anyway. It certainly did to me when I first studied this topic. Okay, so now the equation corresponding, the equation in polar form corresponding with that equation in rectangular form is this. Looks totally different, doesn't seem to be any kind of relationship whatsoever. All right, and I want to make sure we see that we don't try to make a conversion here. And I don't suggest that you go up here and replace x with r cosine theta and y with r sine theta and try to get this equation out of it. After about the 10th step, you're going to probably give up. So we don't want to try to make that kind of correlation. But what we do want to do is this. We want to understand the aspects of that equation in terms of the A, B, and C business. We're going to need that information in order to construct the graph. Now, of course, another way to construct the graph would be to just pop this into the calculator. You just put your calculator on polar form and enter this rascal, and you'll have the graph right away. But we want to make a greater study of this algebraically. All right. We have a 1 in this position. Now, that tells us that our equation is in the form that we want it to be in. And we're identifying then the coefficient of either sine or cosine here as the eccentricity involved in our problem. Now, we're not worried about that minus sign. The plus or minus sign just has to do with position of directrix, so that's not a really big deal. At this point, it's not anyway. So the eccentricity then is 0.8. So E is 0.8. Now, because it's a number that's less than 1, we know we're dealing with an ellipse. If we didn't know it before from all of this information, we know it now because of the eccentricity number. All right. At this point, we can begin to make some calculations. The most obvious one is this, that EP, or if you want to write it as PE, that's okay, but the PE or the EP is the number that's in this numerator. So if EP is 1.8, then dividing on both sides by E, we find P is 1.8 over E, or 1.8 over 0.8, 2.25. Now P, remember, is just the distance from the focus to the directrix. So it doesn't help us an awful lot. It gives us a pretty good feeling about where it is. Since this is a minus sign, it's to the left of the pole. I mean, if we were just starting our idea of graphing, let's just move over here a little bit. This then is the position of a focus point. Now there are two foci, and we're kind of targeting one of them here, but this is one focus point in the ellipse. And we know that the distance, the p-value, the distance from this to the directrix is, the directrix associated with this focus point is 2.25, and it lies to the left. So we could go 1, 2.25, gee, that's about right here. See, we could identify it at this point. But what we're really interested in is the structure of the elliptical curve. We would like to draw the ellipse. Now, to do that, we want to associate the ABC that we've had before. Now, E, we know, the eccentricity is C over A from our study from the past. And we can manipulate this in a lot of ways, and one way to do it is to multiply on both sides by A to say that C is A times E. Now, we haven't jumped from the notion of eccentricity into any of the values for A, B, or C. I want you to notice that right here. And that's the transition we need to make. We need to somehow find A, B, and C in order to structure the graph. Okay, here's how we do that. Now, we know that we have in play also this idea of C squared is A squared minus B squared. We could make some interesting substitutions here, and we could attack this problem algebraically if we want to. I would like to attack it a different way. I think it's more effective and it's more visual for me, and I understand it conceptually a lot better if I think about it like this, you see. And now what I'd like to do is build a table of values and plot some points. Now, I can plot a whole bunch of points, but there are some really important ones to this study, and those points are the points that lie horizontal with this focus point. You know, I know that I have a major axis that's going in this direction. I'd like the point that's at that end of the major axis and this end of the major axis, and then I really have something to work with. Okay, here's what you do. You make a table of values and you say, okay, let's let theta take on values 0 degrees or 0 radians and 180 degrees or pi radians. You see, and use that in our original equation. Let's march back over here and do that. All right, if we're talking about 0 in terms of cosine of 0 is 1. And so we would have 1.8 over 1 minus 0.8, that's 0.2. 0.2 into 1.8 goes 9 times. So this then is 9. And now we can plot a point. And the point we're plotting is 9 0 degrees. So 0 degrees means we're going in that direction a distance of 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, at this point, we know that somewhere in here the center of our ellipse lies. We don't know quite where it is, though, because that's a focus point. And so somewhere in here is the center, and so we have kind of a C value in here, and we have an A value in here from the center to the end of the major axis, you see. So we have an A and a C, and we know that A plus C then is equal to 9, but we don't know very much else. We discover an awful lot by finding the value of R when theta is 180 degrees or pi. When theta is 180 degrees or pi, we have the cosine of 180 degrees, which is -1. -1 times -0.8 is 0.8. 1 plus 0.8, 1.8 in the denominator. 1.8 over 1.8, that's 1. So R is 1 when theta is 180 degrees. And now we think about plotting that point. We think of an angle of 180 degrees and a distance of 1. Oh, that's right here. And now we had a distance of 9 out this way and 1 in this direction. That's a total horizontal distance of 10 for our major axis. So right away then we know that A then is, let's see, 10 for the major axis. Half of that would be the distance from the center to the ends of the major axis. That means it's 5. We have also, let's identify that spot. Okay, so from here over 5, 1, 2, 3, 4, 5, here's the center. So we know this distance is A. We know the distance from the center to a focus point. C is 4. We can easily calculate the value of B using our A squared, B squared, C squared relationship. We find that value to be 3. I'm going to put those values up here. The C value we know to be 4 just by observation here. The B value, when we calculate, turns out to be 3. And now we can construct the graph. So from the center, you see we go up 1, 2, 3, down 1, 2, 3, and we can draw the ellipse. Now, I think the major point of this analysis and using this method is to think about identifying points on our graph, on the curve of whatever kind that it is, by using this table of values and finding points in some direction or another. Now, it wouldn't have helped us a great deal in terms of A, B, and C to identify points that lie up here, because remember, we would be thinking maybe 10 degrees gives us a point out here, and 30 degrees gives us a point over here, and all of that kind of thing. Well, that doesn't help us a great deal in terms of A, B, and C. But directions that are perpendicular with one another a lot of times will give some great information. Not necessarily on this one 90 degrees and 270, but certainly the 0 degrees and 180 gave us all the information we needed about this figure. When we first look at a polar equation of a conic section, we need to write the equation in standard form in order to identify the kind of conic we're dealing with. In this problem, for example, we're not in standard form because this element, this item, needs to be a 1 for us to have standard form. Now, certainly we can identify certain ideas involved in this problem. The plus sign tells us something, and the idea that we have sign involved tells us something. But really, we really start our thinking about the problem by rewriting and causing this item to be a 1. Now, to do that, we'll need to multiply in the denominator by 1/3. So to multiply in the denominator by 1/3 means we also need to multiply in the numerator by 1/3, because we want to multiply by a form of 1 in order to change the form of this fraction but not its value. Okay, in the numerator, 1/3 of 32 is 32 over 3. 1/3 of 3 is 1, and 1/3 of 5, 5/3. All right, now we can identify the kind of conic by looking at the eccentricity. The E value is 5/3. 5/3 is larger than 1, and therefore we know we have a hyperbola. We also know a couple of other things. Now, the sine idea tells us that all of the action is vertical. That is, we have a vertical transverse axis because of the involvement of sine theta. And this plus sign tells us that our directrix is located above our focus point. So the vertical transverse axis, directrix above the focus. We know all of those things now just by looking at the standard form for our equation. Okay, now to start our thinking, we know that our focus point is here. All the action is up here. And with the hyperbola, having a directrix which is above also implies that all of the other major elements are going to be above that focus point, because the directrix tends to lie sort of in the middle of the figure, whereas the directrix in the ellipse kind of lies outside of the elliptical curve. Okay, so we go through and we analyze in a number of different ways. We can identify the value of P by doing this. We found E to be 5/3. The numerator of the fraction is PE, so PE is 32 over 3. Now, dividing on both sides by E, we would find P to be 32 over 3 divided by E. E is 5/3, so 32 over 3 times 3/5 gives us a P value of 6 2/5. This doesn't tell us a great deal about the structure of the hyperbola itself, but it does allow us to identify the position of the directrix. Let's do that. Let's come back over here. If the P distance is 6 2/5, that means that directrix lies above the focus, and it's a distance of 6 2/5. 1, 2, 3, 4, 5, 6, and 2/5 means we're right about in here. Okay, so there's the directrix. Now, the information we need about A, B, and C that will allow us to construct the graph of the hyperbola, we can find by using a little table of values. And because our information, our important information, like positions of center and vertices and the other focus for that matter, lie vertical with this point, then we want to evaluate in our table of values for an angle of 90 degrees and an angle of 270 degrees. So we begin to structure a table of values. Let theta take on values 90 degrees and 270. That corresponds with pi over 2 or 3 pi over 2, as you know. All right, to do that, we can use either the original equation or the standard form of the equation. Sometimes the original equation is a little easier. Here's the original equation, and when theta is 90 degrees, we just think about a 90 degrees in here, sine of 90 degrees, gee, that's 1. So we have 32 over 3 plus 5, that's 8. 8 into 32 goes 4, so R then is 4. And we can come back over here then and add that information into the table. And we can plot the point 90 degrees 4. So 90 degrees, a distance of 4. And that point is on the curve, on one of the branches. And because it's on the transverse axis, we know it's a vertex point. So we have one vertex point right here. We find the other one by evaluating for theta equals 270 degrees. So we come back over here. When theta is 270 degrees, we find the sine of 270 degrees is negative 1. So we have 32 over 3 minus 5. 3 minus 5 is negative 2. 32 over negative 2 is negative 16. So an R value, a distance of negative 16, is associated with an angle of 270 degrees. And so we think about that angle of 270. That means we're turning an angle all the way over here, all the way down here. And then we go negative 16. That means up 16 from that angle. So up 1, 2, 3, 4, 5, 6, 7, 12, 13, 14, 15, 16. Wow, that's our other vertex point. All right, now we kind of know about a little bit about the structure of this thing. One branch is going like this, and the other branch is going like this. The branches tend to wrap around the foci, remember. But in order to get some kind of accuracy in the nature of the graph, we need information about the ABC, and we would like to identify asymptotes and that kind of thing. Well, right here we can see some information about the center, because we need that the B value, is taken from the center, or it can be taken from the center. Actually, we could take it down here because it's only a reference idea. But usually we jumpstart our thinking about these problems from the center. And the center is right in between these 2 points, right in between the vertices. Now, notice that I have information about, let's see, this distance, this whole distance was 16. This distance right here was 4. 16 minus 4, that's 12. That means that this is 12. That means that half of 12 is 6. So let's see, 1, 2, 3, 4, 5, 6 from either direction, you see, would put us right here at the center. So we could identify the coordinates of the center rather easily. Now we have information, just from the graph, we have information about, let's see, from the center to a vertex point, that's a distance of A. So we know A is equal to 6. 1, 2, 3, 4, 5, 6, just calculated it a moment ago. We have distance from the center to a focus point, that's a C value, and that turns out to be, well, we could count to get it, and that would be easy enough, but it's this 6 plus another 4, that's 10, so C is equal to 10. And then from here we could make the calculation for B, and then go that distance this way and make our little rectangle and so forth. Okay, if we were taking a sort of an algebraic approach with this, then we could approach it algebraically in this way. We have this notion of those distances from the focus. Remember that distance of 4, and then that distance of 16. So 4 was the distance to one vertex, 16 the distance to the other vertex. And so 16 minus 4, 12, represents the number of units between the vertices. And half of 12 is 6, so the A value is 6. So 6 units from the center to the vertex, you see, is what we're calculating here. And then the C distance is 6 plus 4, you see, or 10 units from the center to the focus. And now, using our relationship between A, B, and C, we can find the B value to be 8. And now, just from this information, algebraically, we can jump right into the equation for the asymptotes. And we don't have to do this graphically, we can just do it algebraically if we want to do that. Now, do realize, though, that because we have a vertical transverse axis, that when we start to think about the equations for the asymptotes, then we're talking about, you remember it was the slope-intercept idea, but it was a slope rise over run. So it's the A distance is vertical here and the B distance is horizontal. So rise over run is A over B. So the nature of the equations for the asymptotes are plus or minus A over BX, then plus 10. 10 is the intercept, the position for our center, and we know the asymptotes go through that center. Okay, so A is 6, B is 8, so 6/8 or 3/4. So the asymptotes are at y equals plus or minus 3/4 x plus 10. Then we could go back and structure the asymptotes and draw the graph rather easily from here. There is one relationship I failed to tell you about before. I didn't want to let you in on this before because I thought it would draw you away from the graphical aspect of these figures. But it's this relationship. It's an algebraic relationship, and it relates the idea of A with the P and the E. And it is that A is equal to plus or minus PE over 1 minus E squared. Now the plus or minus is here just to make sure that this fraction turns out to be positive. You know, in this situation, our distances are always considered to be positive. We could have just as well put absolute value around this to make sure that that happens, but I'm using plus or minus. At any rate, for the problem that we just had, the PE was the numerator of that fraction in standard form. It was 32 over 3. And the E value was 5 over 3, and evaluating this, we would find A to be 6. And then once we have A, we can just run algebraically into all of the other important information that we need for graphing. E, you know, is C over A. You see the eccentricity is C over A, and we have A. So if A is 6, then we find C very easily to be 10. And if we have A and C, then we find B using this relationship as 8, and bam, away we go with the idea of asymptotes and graphs and so forth. Okay. I didn't tell you about that because I really like the emphasis on the geometric approach and understanding exactly what's going on geometrically, especially in this situation involving polar coordinates. Okay, consider this problem. Suppose we want to find a polar equation of a parabola with directrix y equals -2. Now notice the change, the sort of shift in the emphasis of a problem like this. We started with the notion that we have an equation and we generated aspects of the graph. And now we have information about a graph and we want to generate the equation. Well, we might start our analysis of a problem like this by finding the directrix. We know that the nature of polar equations is that we have a focus at the pole. So we would begin by thinking this way. All right, now we have a directrix at y equals -2. And we have a focus right here. Now the nature of parabolas is that we have a vertex that lies right in between a focus and a directrix. So we have a vertex right here and the parabolic curve behaves like this. So we know all of those things just as soon as we have the information right here. But we're not interested in the graph. We're interested in the equation associated with the graph. And we go about structuring that equation like this. It is R equals, now our just basic idea about this is PE over 1 plus or minus sine or cosine, E sine or cosine theta. Now the sine or cosine, well, we can make a quick decision about that. Because we have a vertical axis of symmetry here, then we know that we have this vertical configuration. That's the idea of sine. So it's sine theta that we want. All right, now what about the plus or minus and what about the PE and all of that business? Well, P is the distance from focus to directrix. And here's the focus, there's the directrix, that distance is 2. Now notice it's not a directed distance once again. It is simply the distance, like absolute value type distance. So it's a distance of 2. So we have 2 for P. The E value is 1. The eccentricity is always 1 when we're dealing with parabolas. And in the denominator we have 1. And then now what about plus minus? Well, the plus minus tells us the direction or where the directrix lies from our focus point. It lies below and therefore we're using negative. If it were to lie above, we would be using positive. So it is minus an eccentricity again of 1 times sine theta. And all we need to do is clean this up. So this is 2 over 1 minus sine theta as the equation associated with this information. This should give us a graph which is a parabola whose focus is here and whose vertex is at -1, 0, -1, and the directrix for that parabola would be down here at y equals -2. Let's verify that idea using the graphing calculator. We're going to use a polar equation this time rather than changing the polar equation into parametric equations. Here's the polar equation, and let's take a peek at window settings before we go on. The theta minimum is 0, max 360 as we might expect, the x minimum -6, the x max 6. I've set a y minimum of -2 and a maximum of 6, and the graph looks like this. Now, the only thing peculiar at this point might be that it's a little unusual to see a parabola come on the screen starting in this position and being drawn up here and then continuing to be drawn down from upper left like this and then joining the beginning point. But the reason for it is the definition for the minimum and maximum for theta. You know, the graph is being drawn according to changes in theta. If theta is 0 degrees, then we draw this point first, and when theta takes on the value of 10 degrees, we draw another point, and then so on. And that's the reason for the graph coming up in the way that it did. We can actually cause the graph to come up in a variety of ways if we just change the settings a little bit. If we cause the minimum to be, let's say 180, for example, then the maximum would need to be, well, let's see, 180 plus 360, that's 540, so I'd make this 540. And then the graph will come up in another manner that might seem rather peculiar, but the graph is coming up in the way that we're defining for it to show up. So anyway, the purpose of looking at the graph is to verify that the equation looks like a graph that we expect. This is a graph that we expect, so the equation is the expected kind of equation that we would have for this kind of problem. Notice that, now remember, the focus is at the origin or at the pole, and this then would be the position of the vertex, and we could find that distance rather easily by using trace. Again, on this problem, we want to find a polar equation. This time we want the equation of an ellipse with eccentricity equals 3/4 and directrix at y equals -2. You know, actually in this problem, we wouldn't even need to be told that we have an ellipse. We could just be told that we have a conic section that has an eccentricity of 3/4, and we would know automatically that we have an ellipse. Well, at any rate, we start the process the same way that we did before. We have the idea that we have a focus at the pole, and if we have a directrix of y equals -2, then here's our directrix. And we analyze the situation in much the same way that we did before. We understand, though, that the directrix associated with an ellipse lies outside of the ellipse. If that's a focus point, then our elliptical curve is kind of up here. We don't know exactly where, and we don't know how elongated precisely, but we have a pretty good idea of where it lies. All right, to structure the equation associated with it, we start with this idea, r equals PE over 1 plus or minus E. And again, it's sine theta because our major axis lies vertically here. And then we go through and identify the various aspects of the equation. P, the distance from the focus to the directrix. Now, again, it is from focus to directrix, and that distance is 2. So P is 2. We're told that eccentricity is 3/4, and we put that eccentricity value in 2 different places in the equation, and that's all there is to it. If we wanted to look at the graph at this point, we could just enter this information into the calculator and have a look at the graph, or we could clean it up a little bit. It's a little easier to enter onto the calculator if we clean it up and take out the fractions. And we can do that by multiplying by 4/4. I'm just selecting a common denominator between the big numerator and big denominator, and multiplying by 4 upstairs we have 6, multiplying by 4 down here we have 1 times 4, 4, and then the 4 takes out this denominator, so we have 3 sine theta for this other term. Let's take a look at this one again on the graphing calculator. The window settings are as they were for the previous problem. I went back to a theta minimum of 0 though, and a theta max of 360, and the x and y maxes and minimums are where they were before. And here is the graph. And certainly the graph is as we were expecting it to be, and the directrix, remember, was found down here at -2. Incidentally, in looking at the figure like this and having some exposure to a directrix and a focus within an ellipse, which is kind of a new idea to us, we might think, gee, if our directrix is down here at -2 and our focus is here at the pole, I wonder if that vertex point is falling right in between these two, that is, in between the focus and the directrix, as is the case with parabolas. Well, we can investigate for that using trace, and we can trace around. We have to go all the way around the circuit here, but it won't take but a moment. We want to go around to 270 and check out the R distance, and if the R distance is 1, our conjecture is verified, but it is not. It's not 1. R is 0.857 and so on. So it is not the case that the vertex is in between the focus and the directrix, at least not for